Hey, welcome back. I hope everybody had a nice vacation. We're about halfway through this set of lectures now. And I'm going to continue the subject that I just introduced before the holiday break, and that is neutrinos themselves. And for me personally, I think neutrinos are the most interesting part of particle physics, maybe physics much more broadly. Certainly they make the link to astrophysics and cosmology. Except for photons, they're the most prevalent particle in the universe. And they're everywhere and come from every kind of source. And so it's a big subject and really an open one because they're so hard to detect that we still don't know as much as we'd like to know about neutrinos. I'm going to touch on several of the subjects over the next few lectures, but I picked to spend a fair amount of my time on neutrinos because I think it's a subject that will make a big impact on physics and astrophysics and cosmology over the coming years, very much like gravitational waves, which I'll come to next. Gravitational waves, because they're so new that we know very little, but we've detected them now. Neutrinos, because they just are pervasive and kind of invade the physics almost everywhere. And then, in their own right, they're mysterious and interesting. They have a little teeny bit of mass. They interact with each other in this peculiar way. And are the product of the weak interaction and so forth and so on. So I'm going to continue on the neutrinos today and through the next the lectures this month, and then go on to other subjects next time. So we're halfway through. It's January 9th, and we're on my second lecture on neutrinos. So in January we'll finish neutrinos. I'll cover subject of neutrino oscillations in some detail next time. I'll try to be, although I'm going to show it on some slides, I'm going to try to not be too technical, but to talk about neutrino oscillations, which is a part of the subject, I have to show the formulas. So I'm going to have them there so you can look at them on the slides, but I'm not going to actually go through them in much detail. Today, though, I'm going to talk about more framing the whole problem and some particular issues of how many neutrinos there are, and so forth. So for January, we're going to do neutrinos, and then we'll move on to my own subject of gravitational waves in February and March, moving ourselves into astrophysics and cosmology as we finish the set of lectures. Okay, so we're on this. I've used this slide every single lecture since the beginning. We've studied the other pieces, and now we're on the neutrinos. And so we're studying the three neutrinos, the neutrino that's connected to the electron, the neutrino that's connected to the muon, the neutrino that's connected to the tau lepton now. And the fact that those three neutrinos are actually different from each other is an interesting fact in itself, and the fact that they're individualized and that we know that, let me just briefly show you again. And that is, the history goes back to the 1930s, or even before, when there was a mystery. And that mystery is that in a well-known phenomenon, just beta decay, a decay of a particle that gives off electrons, the electron spectrum that was observed, which is shown here, is continuous. The maximum energy that could go off into an electron is out here, but it's continuous. And so what that means is you started with some radioactive element, it decayed into another one, and should have just given a beta particle of half an MeV. But it gave, if that were true and it was a two-body decay, then the electron, this particle here, would have a unique energy all the time. But instead it had a spectrum, and this was a big problem in the 1930s. I talked about it last time. It caused huge debates about whether conservation of energy was somehow being violated and didn't apply, and so forth. In the end, it was actually the fact that there's another particle emitted in the radioactive decay, that is the electron, that was proposed first by Wolfgang Pauli. He did it, as he says in this letter, pretty much out of, he uses the word desperation. And that is, in order to conserve conservation of energy, he had to assume that another particle was emitted, but that particle had to be neutral. He called it a neutron. That's a misnomer because the neutron was discovered 2 years later and is a different particle. So this is the neutrino, even though he calls it a neutron here, and that would solve the problem that there was yet a neutron or neutrino emitted in the decay of a proton to a neutron and an electron and a neutrino. So, of course, that was discovered later. By 1933, the neutron had been discovered. It was discovered by Chadwick in 1932. And, of course, then this becomes the neutrino. Fermi then entered the picture by writing down for the first time a theory or a description of what happens in this beta decay, and he developed what was called the Fermi interaction. And that would be the interaction that would characterize not just this in the future years, but essentially weak interactions, the decay, the radioactive decay of any particle that gives a radioactive decay in the future years. And this was done until more advanced theories, including using quarks and so forth, were developed. And finally, the electroweak theory of interactions 20 or 30 years later. This was the best picture of the interaction that caused the weak interaction, which was used for years, developed by Enrico Fermi, actually in 1933. And the strength of it is the thing that I write here as GF. And that would tell the strength of the weak interaction, which is, of course, much weaker. That's why he uses the word weak, compared to the electromagnetic or the strong interaction. The fact that there was a neutrino needed to be not just shown as an answer to the fact that beta decay gave this spectrum, but actually seen in the laboratory. And that was done finally 20 years later, roughly, in the 1950s by Reines and Cowan. And last time I showed the history of that, how they originally thought the right way to do it was to actually detect the neutrinos that came off in an atomic blast when they were doing atomic testing at that time. And eventually they were directed to study it and using a nuclear reactor. And first they went to Hanford, where there was a nuclear reactor, and did an attempt to see the neutrinos interact that was not definitive because the backgrounds were too high. And then they went to the Savannah River nuclear power plant, where it was possible to have a much more shielded device. And there they were able to actually see for the first time in a convincing way that there was this new particle called neutrinos. The flux of neutrinos is really high. So in order to think it would be easy to see that there are neutrinos, realize that around this fission reactor, there are 10 to the 13 of them coming off every square centimeter every second. So there's a lot of neutrinos coming out of these machines, yet they're so hard to detect because the interaction is so weak. This is a picture of what they detected here. So the neutrino comes in. So neutrinos are made in the fission reactor as a product of the reactions that happen in a fission reactor. They're outside the reactor and put up a detector where the number of neutrinos coming out is something like 10 to the 13 per square centimeter. They're quite low energy, but they're a few MeV in energy. They come out, and a neutrino schematically comes into a detector, which in this case was a mixture of water and cadmium. And it interacts. When it interacts, it makes a positron and a neutron. This reaction is just, if you move the neutrino to this side, it becomes an anti-neutrino, is just the beta decay of a proton. So this is looking at the beta decay of a proton, but looking at it as a reaction. A neutrino hits a proton, makes a positron and a neutron. To detect these, the reaction here makes a positron and a neutron, which is shown here. The proton doesn't go very far. The neutron then interacts and gives off a delayed signal from a gamma ray that's made in the interaction. This is a product of the fact that the neutron makes something heavier, and that has a decay time that's later. So the trick is to not look at the same time that everything happens, but look later for a photon that is emitted with that is emitted always a certain amount of time after the signal itself. So the basic thing, the neutron then is discovered by the fact that it comes out later and makes an interaction that's detected. The photon that came out, the electron that came out, actually finds another electron. An electron and a positron annihilate. When they annihilate, they make two photons, and those photons are observed. So this is looks like a very good and very unique signature. There's 10 to the 13 of these coming out, so it seems like it would be very clean and interesting. But you'll notice in the first discovery that they barely see in a convincing way the interaction. They ran for 900 hours doing this, and they saw one event that looks like this every hour. When they turn it all off, so that there's no real neutrinos coming, they still see a quarter of an event per hour. That's because neutrons are coming from everything, not just from the reactor. Neutrinos are, sorry. And so there's a lot of background. It's hard to detect neutrinos. It's a big, big challenge. So when they failed to do it at Hanford, it's because these two numbers were much closer together. This is just convincing enough so that they made the neutrino discovery. They turn off or they turn on. Every time they turned on, there were roughly 4 times as many events as when they turned off. But they still had a fair number of events when they turned off the reactor itself that was making the neutrinos. So this is the first actual discovery of the neutrino itself. And of course, that neutrino is the electron neutrino when we go to the picture here. The muon neutrino, so that's the electron neutrino. The muon neutrino, which is here, was discovered by these 3 guys. And it was years later. So we started in the 1930s with this whole problem. Now we're in the 1960s. And in 1962, the second neutrino was discovered by Schwartz, Lederman, and Steinberger at Brookhaven National Laboratory, using when I talked about accelerators, alternating gradient synchrotron. Remember I talked about how you focus a machine by having a gradient across it, which is opposite to each other, and that creates focusing. They then made a high-energy particle beam that protons interact and made high-energy pions. So these are all pions, you'll notice. And when the pions decay, they always make the neutrino that is associated with a mu meson. So it's pi, the decay channel makes a pi and a muon. So the decay particles that enter here are always neutrinos that were associated with the production of mu mesons, like the second channel that we had, second article that we had. And what they saw in their detector was that interactions always of these neutrinos they've observed years enough later so they could do it pretty well. They observed them cleanly, but they always produced a muon and never an electron. So somehow these neutrinos remembered how they were born. If they were born in association with a muon, they made a muon in the final state. If they were born as a product of an electron, they remembered they were an electron. So therefore, these neutrinos are given this little subscript, nu sub mu, and in terms of the three neutrinos, we now have established that these two were different from each other, and they're given a nu e and a nu mu. The third neutrino is associated presumably with this last column of quarks and leptons, and it is of course a column that's much more difficult. If you remember, the top quark was only discovered in 1998 or something like that. It's very, very heavy, and the bottom quark somewhat later. So this whole column we know less about than the others. The tau lepton was actually discovered, I showed you that, at SLAC in the same time as the famous J and psi particle were. The tau neutrino was a very big challenge to detect. And you might say that because we found this whole set of quarks and so forth, we've seen this one and this one, do we really have to see this in the laboratory? And the answer is definitively yes, because of the fact that experimental physics and theoretical physics work together such that you need to not just infer something because you believe it's there, but also observe it. And we've learned in enough lessons in nature that it's important to do both. Even though you think theory is right, you need to try to observe experimentally, or if you observe something experimentally, you need to be able to explain it theoretically. And to make the whole picture of physics work together, you need to be able to do both. So we need to be able, even though it was a big challenge, to actually see if we could establish that a tau neutrino existed in its own right. And that was an enormous challenge to do experimentally. Maybe a kind of thankless job, but to do experimentally. And that was taken on at Fermilab in the year 2000, so within the last 20 years. And like the muon neutrino, it has to be connected to its charged lepton. We said that the muon neutrino always came associated with a muon. So the tau neutrino will always come associated with the tau lepton. The lifetime of the tau lepton is very short, however. It's 10 to the minus 13 seconds, which means even at high velocities, it'll only go 90 microns, something like that, in space. So you can't have a big detector big enough to make these things interact and still see where these particles went without having very, very, very small, tiny resolution. So that was the challenge. The experiment that was done was called donut, like a donut that you eat. And that stood for direct observation of nu taus. And just for numbers, out of, if you have 10 to the 13th neutrinos, only 1,000 of those neutrino interactions will be recorded. And out of those, only 4 were identified as tau neutrinos. So basically, they had to study a huge number of neutrinos to even get a sample that you could look for charged neutrinos. This is the schematic of how the experiment was done. A photon beam is brought into a big place where the beam itself is dumped into the target. Out of that, charged particles and neutrinos are made. There's a big shielding wall so that something like out of 10 to the 17th protons that enter here, 10 to the 17th is a big number. only about 400 neutrino interactions are finally studied. And out of those, only 5% of them are new taus. So the numbers are very small. Secondly, the new taus have to be studied because they don't live very long over a very short space. So the way it's looked for is that a neutrino comes in, it interacts, it makes the tau lepton, and it only lives so far and decays and gives the new tau, and you have to measure this lifetime. In order to do that accurately, the only technique that I've shown you that is able to measure very, very short distances is emulsions. Emulsions are a very difficult technique to use because it has no intelligence. If I make a lot of the detectors that I showed you, what makes them very sophisticated, other than all the electronics and so forth, is that you can put some intelligence in. It records data that you teach it to record that has something to do with what you're looking for. An emulsion is just a piece of film that takes pictures of whatever. It just records the tracks of anything that went through it. So an emulsion target is in itself not very smart, but it's able to measure the very, very short distances to be able to see this kind of picture, which is what was looked for. And that they succeeded in the early 2000s to make the first observation. I only show this picture to show you how big and complicated an experiment has to be in order to measure something that's so small. So this is the big experiment done at Fermilab to do this with a neutrino beam coming in, and it's roughly 15 meters long and 15 meters wide with all these different detectors, and in the heart of it is the emulsion stack that then has to be analyzed to see these very little tracks. The rest of it is just picking out the interactions that would be candidates to give the neutrinos and where the other particles went in the final state, the tau lepton itself and the other particles that happened in the interaction. So that's the third neutrino. This is just another picture of it. This is a picture of the emulsion track itself, the tracks, seeing the little kink that I showed you that was a signature of this particular interaction. Okay, so we have then the following situation that we now have seen in many different ways, now in this way as well, that we have this set of particles. These are the force carriers. These are different than these particles. This is just an indication of the electromagnetic, the weak, and the strong force, that we have three levels of matter particles that consist of what makes up matter. The normal ones that we know about and make up most of what we know, of course, are these, but there's two more for what reason we're not sure. And we now know that we have seen and identified all three separately and differently of the neutrinos that go along with these. These will be very important as I move on in these lectures because they interact with each other, as we'll see. Then we have all three of them. We don't know why there are three, and we don't know why only three. So we don't know first why there aren't just one set of elementary constituents that make up matter and the forces. And if there's more than one, we don't know why there's only three, for example. Or are there only three? So we don't have a good answer. That's something that hopefully we'll learn in the coming times, but we really don't know that. You might ask the question, are there really only three? Would there be more? And the evidence that there are only three, I showed you. And that is that if I take an electron and a positron and I collide them at high energies and they make a pair of, say, muons, and I make a plot of what the muons look like, that's shown here. So I bring in an electron and positron. This is in the Feynman diagrams that I've shown you. And they collide together. And I change the energy from 88 to 90 to 92 to 94 to 96. The cross-section, or the probability of interaction, gets larger and then smaller. This is the result of having the Z particle, which carries the weak interaction in between. The width has to do with the strength of the Z particle, which is shown here. I can show, and I showed you once before, but I'll repeat it here, that the width of this depends on the number of ways they can interact. So if they interact here and make a pair of muons, that's one possible channel. If it makes a pair of electrons, it's the second possible channel. If I add up all the channels, then I get the number of decays. If there are more channels, then the width of this will change, because if it's more probable that it'll decay, it won't be as uncertain. This shows the three curves here are the widths that it would have if there were only two neutrinos, 3 neutrinos, or 4 neutrinos. And you can see that the data points, which are shown here, fall very nicely onto 3 neutrinos. So this is the experimental evidence, if you want, that there are 3 neutrinos in nature. Therefore, presumably 3 families, as I showed you, of quarks in nature, that there's 3 of them, which is experimentally shown, not just because we've observed those quarks, but because the interaction of the Z particle itself gives this width. That's almost true completely, but not quite. If you had neutrinos that were more than half the mass of the Z particle, then they wouldn't do anything to this curve, because you have to make 2 of them in the final state. So one condition is you could have neutrinos that somehow don't fit this picture. One possibility is that they're too heavy. Of course, the neutrinos that we have so far are extremely light, but maybe there's some sort of neutrino that was very heavy. Or maybe there are neutrinos that have a different kind of interactions. And that's the ones that people are looking for very intensely. And there's some evidence, which is not perfect, that there may be such a neutrino. I'm going to show you that evidence, because it's one of the open questions, I think, that since we're supposed to be covering the frontiers of physics, that hopefully will be answered in the coming decade, and you can keep your eyes open and see what happens. So I'm going to show you the evidence that exists, which is, it's intriguing, but maybe wrong. So to address the question of how many neutrinos there are, I have to present kind of in advance a little bit the fact that neutrinos, the 2 features that I haven't talked about. And those I'll address somewhat, as I said, more completely and more quantitatively in the next lecture. I'm going to just show you a little bit today so that I can show you the question of how many neutrinos there are first, since we're talking about 3 neutrinos or 3 families. And but there's 2 features of neutrinos that we'll talk about more next time. So if you're not satisfied with what you hear now, I'm going to talk about it more. First, something that we never knew had to be true or was true until very recently, and that's that neutrinos have mass. That isn't required by the Higgs particle. So neutrinos being massless was more or less assumed for 50 years. Once we saw there had to be something like neutrinos, it was assumed they didn't have any mass, although there was one indication that neutrinos could have mass and could change their identity, which was actually an idea put forward by Bruno Pontecorvo 30 or 40 years before it became actually true. His motivation actually came from something that turned out was wrong. Secondly, if they have mass, it turns out, and that's what I'll show you next time, that they can change identity. Kind of mysteriously, if I have a neutrino going along and it's what I told you I found as a muon neutrino or an electron neutrino, and just let it fly, it can change its identity and become another kind of neutrino. And I'll show you the puzzle today of how that was discovered and that it's true. That's called neutrino oscillations. that it can change its identity from one kind of neutrino to another kind of neutrino. So even though I said there are three kinds of neutrinos, and I said they're different from each other, they belong in those three families, what isn't true for the quarks or the other leptons is that these aren't so pure. They actually can change identities one to the other in some curious way. And that's what we'll spend time on in the next lecture. So we'll return to this in the next lecture when I'll talk about neutrino oscillations. I'll talk about it only enough today to make you kind of realize that what you don't understand, you'll hopefully get next time. I mentioned when I introduced the topic of neutrinos that neutrinos are pervasive and essentially everywhere and come from everything. So the physics of neutrinos, once we can understand them, affects almost everything in nature that we talk about. So neutrinos come from what we call atmospheric neutrinos. That's neutrinos that actually come about from cosmic rays that interact in the atmosphere. And there's a lot of them. There's about the time that it takes for those neutrinos. These times I'm giving here are important when we start talking about the fact that neutrinos can change identities one to another. When I talk about these different sources, you have to realize that how much they kind of mix these neutrinos together is going to be different depending on which source I'm talking about. So if I make neutrinos in the atmosphere, it takes only 10 to the minus 4 seconds, something like that, for that neutrino to get to the Earth. The atmosphere is not that thick. If I talk about neutrinos that come from the sun, it takes about 8 minutes for the neutrinos to get to us. If I talk about neutrinos that come from a supernova somewhere, it's 10 to the 4th years, and so forth. So I talked about early universe is 10 to the 12th years. So these neutrinos, because of the fact that they mix together and so forth, they're going to have rather different features depending on what the sources are, in addition to different energies and so forth. So these neutrinos affect the physics or the astrophysics or the cosmology all the way from kind of neutrinos that are made in reactors, made in the atmosphere, made in the sun, and so forth and so on. I divided it here into natural sources, and you can see that it's all over the place from kind of the sun to supernova to the inside of the Earth, and ones that we actually can make ourselves, which helps us when we try to do the physics because we can control the neutrinos we make and understand them in a better way than when they come from other sources. So we have two ways to make them man-made, and I'm going to be talking about both when I talk about neutrino oscillations. First, on nuclear reactors. The reactions that happen in nuclear reactors produce a lot of neutrinos. That's what was used in the evidence for the discovery of the neutrinos. And there, typically, the amount of path or time it takes for those neutrinos to get from the source, the reactor, to the detectors is pretty similar to what happened in atmospheric neutrinos, something like 10 to the minus 4 seconds. So in terms of kind of whether they keep their own identity and so forth, that's the case. On particle accelerators, as the second way to make them is something like 0.001 seconds. So these are the different ones. We're going to talk a little bit about the science of those different ones where I think the problems are interesting, but not kind of go through them one by one. Today, I'm going to pick just one problem, and that is solar neutrinos. That is neutrinos that come out of the sun. And we're going to talk about neutrinos that come out of the sun because that is basically the historical way that we first understood that we understand the burning cycle of the sun. Secondly, that it didn't make sense what was seen in neutrinos and had to be understood. And third is that to understand it, that actually is what gave us the insight to see that there had to be something like neutrino oscillations, the subject that we'll talk about next week. So let's talk about the sun a little bit first. We see the sun all the time. But let me just talk a little bit about what the sun is and what the image is of the sun is just kind of a side thing. So this is a visible image of the sun. It's a big ball lit up in the sky that we see with little dark spots on it occasionally, like that picture here. It's our sole source of light and heat in the solar system, so it's obviously important to us. Our sun is rather common. By common, I mean it's not a very different star from all the stars that are seen when we look at the sky. It's our star. It's quite common, except that it's pretty small. So compared to most stars, it's on the small side. So, but it's a star like many stars that we see, and there are other stars that are the size of our sun. But basically, it's small compared to, say, the average size of stars. What is it? It's a glowing ball of some sort of gas held together by gravity, because the gas is made out of nucleons and particles and elements that are held together by gravity pulling on it, and so it basically it doesn't disperse in space because of gravity, and it doesn't go into a tight point as gravity tries to pull it because of the fact that it is itself creating an outward force which comes from what we believed and believe is a nuclear fusion interaction at the center of the sun. And this is not just the sun, but the same thing we believe about all the stars. So I'm talking about the sun, but it is the same process that happens in stars. So all stars, we believe, have gravity and matter, but inside of it, the matter and gravity is trying to pull it together, and there's an outward force, and it stabilizes at a certain size that is created by a nuclear fusion process, which is creating the energy and the heat that is made in an outward force that's made in a star. And ours has the same thing, but basically, let me go through the numbers for our own star. So during the burning cycle, while somewhere in this middle part, there's a nuclear fusion reaction, we have gravity pulling in, and we have a pressure outward that comes from the fusion reaction. And that's an equilibrium that's the size of our sun itself. So the pressure from heat results from the nuclear reactions, and it's balanced by the gravitational pull toward the sun's center. That's the hydrostatic equilibrium that we're in. And this balanced state is just this large spherical ball of gas that we call our sun. This continues, and we happily watch the sun. It seems the same every day. It continues until the sun burns up all its fuel, just like a car burns up its fuel or whatever. At that point, the sun has lost its outward pressure, and so it collapses. And that's what we call a supernova. What it collapses into, I wrote down here as 3 question marks, is different depending on what the features are of the sun itself. For our sun, we don't know what it'll end up in the end. It may be brown dwarfs or other things that we see in the universe, but we're not sure. Heavier stars, if they're heavy enough, actually give a black hole, and those black holes are presumably the ones, we call them stellar black holes, are the ones that were discovered and seen in the gravitational wave experiment that I've done that I'll talk about in a few weeks. So there's black holes that were made. They're a mathematical concept, but they're also a physical concept, and we know how they could be made by the collapse of stars. But the star, in order to do that, from everything we know today, which may not be exactly right, but everything we know today, a star has to be at least 3 times the mass of our sun in order to, when it collapses, have such strong gravity that it's a black hole. And I'll talk about that in a few weeks. So when our sun collapses, it won't make a black hole, that's for sure, because it's too small. We're not sure what it'll make. But that's basically the equilibrium between gravity and pressure. So it's happily going along. We don't have to worry about that yet. It'll live for a while longer. This is the dimensions in the sun of the different regions where something's happening. So the core, what I call the core, which is about 200,000 kilometers in the middle, is where this nuclear fusion reaction is happening. So the fusion reaction is basically the engine that's making the sun make the heat and light that we live by is happening in here. That makes then a series of regions, a region that's called the radiation zone, then a second region which is called the convection zone, the photosphere, the chromosphere, and so forth, and finally something we call the corona and solar wind. Just to give you some picture of that, I'll quickly show you what those are. So first, the sun itself. How big is it? I made it sound small compared to other stars, which it is. It's a smallish star, but it's big compared to things that we're used to. So the sun itself is something like 100, the radius of it is about 100 times the radius of the Earth. So it's huge. I drew a picture in the middle of the Earth to scale compared to the sun. So the sun is much, much bigger than the Earth, 100 times bigger in radius, of course in volume much more than that. The mass of the sun, the mass, is 300,000 times the mass of the Earth. So the amount of mass that's in the sun is huge compared to what we're used to in the Earth. Black hole has to be something like 10 million times the mass of the Earth. The average density of the sun is 1,400 kilograms per meter squared. And you can think of kind of, per meter cubed, I'm sorry. A meter cubed is like this, and you're talking about it being 1,400 kilograms for that length. So it's quite dense matter. The rotation period is interesting. So this is just, because you live with the sun every day, I decided to show you some of the features. Did you know that the sun basically rotates at a different period near the poles than it does in the equator? That's not true of the Earth, of course. The Earth, we rotate one rotation at in Iceland when we do run one rotation at the center on the equator. That's not true of the sun. The rotation at the center is 24.9 days for one rotation, while the rotation, if you move up near the poles, is something like 29.8 days. A lot of the dynamics that we see are due to this difference in rotation rate. So the size, again, I've shown before I change slides. If you take the moon's orbit around the Earth, it's all contained within the size of the sun. So to emphasize kind of how big the sun is, even though it seems small in the picture, it's quite big compared to the sizes that we're used to on the Earth and the moon. The surface temperature is 5,780 degrees Kelvin. So it's hot on the surface of the sun. Of course, we know that. Now, how bright is the sun? We measure it in terms of luminosity. Luminosity is how many photons in energy are emitted per second. And the luminosity of the sun in units that we like to use is 4 10 to the 26 watts. That's equivalent to 100 billion 1 megaton nuclear bombs every second. That's how much energy is being emitted from the sun. That's a lot. We basically take that amount and take the amount that reaches the Earth, and when you read something on astronomy, you often find that people talk about astronomical units. One astronomical unit, so you know what it is the amount of sun energy that gets to the Earth at that distance. So you take it and divide it by the square of how far away the Earth is, and that's the amount of what is called one astronomical unit. Okay, Now, if we want to learn about the interior of the sun, that's called helioseismology, then people do a lot of research on this, and there's solar physicists that do a lot. I'm not going to do it justice. I just want to give you some sense that the sun is a complicated object. In the 1960s, it was discovered that the surface of the sun is actually vibrational. It changes. Vibrational, but vibrational in a ringing way, much like a bell rings. The internal pressure wave reflects off what I call the photosphere, and that's what causes this bell ringing. And that's kind of how we study things on the surface and infer what they're like inside. Analysis of the surface patterns and the waves are what tell us what's happening inside the sun. We have no way to penetrate directly inside the sun. This is a picture then of the temperature in the sun. If you go to the very center where we have the nuclear reaction, the fusion reaction, it actually has a temperature of 15 million degrees Kelvin. And the temperature at the surface, as I showed, is about 6,000 degrees. So even though the surface is hot by our standards, it gets hotter and hotter as you move in toward the center of the sun. And of course, the density, again, at the surface is just a gas. And so it's quite light, not very dense. While at the very center, the density is about 150 grams per cubic centimeter, which is significant. So that's basically a picture of what happens as you go inside the sun. The transport, which is mostly inferred by what happens on the surface, from the engine that makes the heat and the energy, the nuclear fusion reaction in the center, transports itself out to the outside through different zones that solar physicists talk about. First, the convection zone, that is not what's made in the core, but what's kind of carried out through convection and radiated out, and then through the zones beyond that, which are the radiation zone, the photosphere, and so forth. So the core is extremely hot, and it's mostly ionized gas. No electrons are left on the atoms to capture photons if you go out a certain distance, and therefore this radiation zone is just transporting the energy out. It's transparent to light, and so there's this zone that's carrying it out. Eventually it gets to what's called it gets less high temperature, and basically then gets to what's called the convection zone, and the convection zone then captures the photons. The gas becomes opaque to light, and that's what we call convection. The low density in this photosphere then makes it transparent to light, and radiation again takes over at the very outside, and then we get the surface part at the very outside. The surface of the sun itself, when you look at it in any detail, is very granular. It has dark spots. It has all kinds of features, and those features are what's used to both study the sun and its features itself, but to infer what happens inside the sun. So these granules are basically the tops of what are called convection cells. The bright regions are where hot material is actually getting up to the surface, and they have a scale. They're about 1,000 kilometers across. The dark regions are where colder materials are actually sinking back into the sun, because convection works both ways. So that's the surface thing. As we move out to the chromosome, we're getting out near the outside now. And here, region out here, then by that region, we're starting to be able to study it, for example, in solar eclipses of the sun. So looking at the solar eclipse of the sun, the chromosome, we see warm jets of matter that shoot out at about 1,000. They're seen when the people study it at something like 1,000 kilometers a second. They only last for minutes. They're from magnetic disturbances, and they emit very little light because they're low density. And again, this is used to study what the features are of the chromosome. The transition zone, which is almost now near the surface of the sun, is studied. It's very low density. The temperature is something like 10 to the 6, a million degrees Kelvin. This is the temperatures, by the way, all the way into the distance all the way from the beginning into the core. And we see that the emission lines from heavy elements like iron indicate that the temperature in this zone is very, very hot. The corona, which is the outside, and everybody's seen something about the corona, again, is actually heat or gas that escapes the sun itself. So when we talk about something called the solar wind, it's actually not just light and heat that escape the sun, but gas itself that gets away from the sun. That's something we call, in the end, the solar wind. So this gas has enough heat and kinetic energy to actually get out of the sun. And the sun is evaporating away due to this wind. So when we say that there's a solar wind, the sun is actually evaporating away. The wind travels pretty fast, 500 kilometers a second, which means it reaches the Earth in about 3 days. So constantly, the Earth is shedding some material through gas escaping. That gas gets to the Earth in a period of about 3 days, and the amount is a lot. The sun loses 1 million tons of matter every second. Fortunately, the sun has a lot of matter, so that doesn't really say very much, because in the sun's total lifetime since it was born, it's only lost about 0.1% of its total mass. So although it's a lot of gas and so forth is emitting all the time, the sun is big enough that it'll still live a while. Now the surface, let me just finish the side story about the sun by the fact that we see something called sunspots. So when you look at the sun, there's these spots on them. This is a photograph of the granulations around a sunspot. You can see they're quite complex. They're typically about 10,000 kilometers across. There's a big black spot that's 10,000 kilometers across. And any time the sun may have none or may have lots of them. So it changes with time. It's dynamic. They're dark color because they're cooler than the photospheric gas than the photospheric gas otherwise. Each spot actually has a lifetime, but they're pretty short. So when you see sunspots, they last for days or maybe a month, but not much longer. And it was Galileo that first observed these spots, and he realized the sun is rotating. He realized from these spots that the sun has this differential rotation that I talked about 20 minutes ago, and that is that the period around the center is less than the period around the poles. And that was first actually determined or observed by Galileo. The sunspots themselves are due to magnetic fields, and they come in pairs. And the pairs tend to be at the same latitude. So they look like the picture here, where you have a north and south pole kind of together, where there's magnetic field lines. They're separated from each other, but you can see both generally. And the magnetic field in a sunspot is about 1,000 times greater than the magnetic field anywhere else on the sun. So they're in specific places and are a big effect. Sunspots are almost always, at least in pairs that we can see at the same latitude, with each member having the opposite polarity in terms of the magnetic field. And all sunspots in the same hemisphere have the same magnetic configuration. That is, these down here are south-north, south-north, while up these go north-south, north-south. So they're the same configuration, depending on whether they're north or south of the center of the sun. The last thing that I'll mention is that the sun has cycles. And those cycles are basically 11 years. There's a solar maximum every 11 years, and a total cycle is 22 years long. And during that period, the direction of the magnetic field flips. So the sun has this feature that the magnetic field is in one direction, flips in another direction every 22 years. After 22 years, it's back to its original. So after 11 years, it flips, then it flips again back to the original in 22 years. This is just some measurements of that were made since 1900, and it's very consistent that it takes basically 11 years for a solar maximum, or 22 years total. Okay, let's take a break, and then I'll go on to talking about the core and the fusion reaction, which is back to the neutrino story.